Hello everybody, today I'm going to be talking about performing a chi-square test for independence. On the last two videos I tested for goodness of fit, I test for homogeneity. Okay, and today I'm going to be doing the test for independence. It's important to know that these two tests, the homogeneity and the independence, are very similar. They're very similar. Okay, so let me go ahead and describe how you're going to get this. They're going to give you two variables, and those variables have to be categorical. They have to be categorical. These cannot be done. If they were quantitative, you'd do a whole different test. And you have to at least have two rows and two columns. Okay, we call this a two-way table. Two-way table. Two-way table is made up of rows and columns. Okay, so this would be category 1, category 2, and so on. For variable 2, we could have all the way up to category n. Okay, or I'll call it category C. We could have C columns, and same thing here, category 1, category 2, all the way up to category R, and R stands for the number of rows. So the question is one great way to determine if this is an independence problem is they give you these two variables and they ask if they're independent. They ask if they're independent. A few other ways they could ask you is they could ask you if these two variables are associated. Okay, another way they could say, are these two variables related? Are these two variables related? And remember, you're going to have your observed in all these boxes. Okay, your observed amount. So for example, I'll just give you a quick example. I'm not actually going to do it, but I'll just give you a quick example. Is I could say, okay, well, I have girls and I have boys. Okay, so these are my two categories, and I'll call this gender. So my first variable is gender. Okay, now my second variable will be shoe preference. Shoe preference. So I could say they're going to wear shoes. They could wear sandals. Okay, so quickly, how many rows do you have? We have 2 rows, and we have 2 columns. 2 rows and 2 columns. Okay, so the question could say, is shoe preference independent of gender? Or another way they could say, does shoe preference depend on gender? Okay, is shoe preference associated with gender? Okay, and it's important to note that the null, I'll get started with the null, is that variable 1 is independent of variable 2. And the alternative is just the opposite. Variable 1 is dependent on variable 2. So that's how you do it if you want to do it that way, if the question kind of asks that way. So let's say we have this thing, and I'll go ahead and do this as observed and expected, because we'll need the observed and the expected for to get our chi-squared. So this is the observed, that's the expected. So let's say we have 100 people total. So we have 100 people total, and we'll have 40 girls and 60 boys. And out of those 40 girls, okay, we got 10 wearing shoes, and I got 30 wearing sandals. Out of these 60 boys, we'll go ahead and say we have 40 wearing shoes and 20 wearing sandals. Okay, so we'll get back to this question later, and go ahead and go to our assumptions. Okay, and for here, all we need is that the expected counts for all cells are greater than or equal to 5. Okay, we're not actually going to take a sample and say something about the population, so we don't necessarily have to have an SRS in this case. Okay, so next would be getting the chi-square, or naming the test. Let's name the test first. So this would be a chi-squared test for independence. Okay, so this is important. Okay, this is the most important thing. I'm going to do another video just on the chi-squared because there's two ways to do it. You could use your calculator, or you could do it by hand and use your book and use a table. Okay, to make your rejection, to either reject or fail to reject. So if we look at this, this is the formula for the chi-squared. So it's the observed minus the expected, and I want to go ahead and square that. And these are i's, by the way, because my I will start at 1, that counts for my first cell, and it'll go to R times C, which is the number of rows times the number of columns, which will give you how many cells that you'll actually have. Okay, so if you haven't watched the other chi-square test for homogeneity, you might have missed this, but the observed equals the row total times the column total divided by n. So for example, if I was going to find the expected for cell 1, comma 1, that's this cell right here. So I'm looking for this number here. What I would do is find all my totals. So I'm just adding here and adding here, 50 and 50. And then I would say the row total for this one would be 40 times 50 divided by the total, which is that. And it looks like this is just going to be 9. I just did 50 times 40, which should be, oh, it's not 9. Sorry. Okay, I'm thinking maybe it's 20, but let me just pull this out to double check. 40 times 50 is 2,000. 2,000 divided by 100 should be 20. Okay, so there you go. It should be 20. Should be 20. Okay, so this in this expected would be 20. And you can continue and find all these expecteds, and that's where these go. Okay, so the first term in this one would be 10 minus 20 squared divided by 20. Okay, and you get the chi-squared. Okay, so that's your t. Okay, the next step would be to find the p-value. We need to find the p-value. There's two ways to do this. If you watch the other video when I talk about the chi-square more in depth, I'll show you how to reject using the table. So the p-value is the probability that chi-squared is greater than what you found. That's what it is. It's the probability you're going to get a chi-square that or greater given the null is really true. Given that the null hypothesis is really true. Okay? And remember, when you do this, there's always a degree of freedom. And the degree of freedom is the number of rows times the number of columns. Okay? Because every degree of freedom is a different shape. So the first degree of freedom might look like this. This would be like degree of freedom equals 1. But if you get into degree of freedoms of like 20, it'll be more traditional chi-squared skewed to the right. Okay, with this being the area. Okay, so how do we make our decision? Our decision depends on what our p-value is. So if our p-value is less than alpha, we're going to go ahead and reject the null. We're going to reject the null. And if the p-value is greater than the alpha, we're going to go ahead and fail to reject. That means that they are independent. Okay? And then go ahead and make a statement. Statement in context. Okay? And a little precursor to the other video, if this is my chi-squared, which is skewed to the right, this is the other way that you wouldn't do it for, this would be the other way if we're not using p-values. So you have some alpha here, and that's going to be our rejection percent. Okay, so for this alpha, if you look on a table, you are going to get a chi-squared with the degree of freedom for that given alpha. Now, if you notice here, these are the two options that your chi-squared, this is the one that you found. So the chi-squared could fall here, or it could fall here. So this is the other way. You compare your chi-squared with the critical value. That's what we call it, a critical value. This is the critical value, degree of freedom alpha. Now obviously, if it's over here, anywhere over here, we are going to reject. If the chi-squared is less than that critical value, and you find this in the table, which on the other video I'll pull the table up and show you, this would be a fail. Okay, so degree of freedom, this is the chart. So if your chi-square falls here, it would be a fail to reject. It's not, and we'd find that they're independent. Let's just take one more quick look over here. I'm also going to be doing an example, a regular example with an independence problem, so be sure to check that out, because I'm going to show you how to do it on a calculator, and I'm going to show you how to do it by hand. So that's it for the chi-square test for independence. Thank you for listening, and have a nice day.